Hello everyone. Well, in this recording I'm gonna cover lecture 12, which is about chapter 11. Alright, in this lecture we're gonna be talking about local area networks or LANs. Right. So what is the LAN or what are the LAN technologies? So if I am uh, going to explain this, I'll start with the idea of when we talked about communication. We started by talking about mostly point-to-point connections, right? So we talked about having two nodes talking to each other using medium. A medium could be a wire, copper wire, could be fiber, could be air, could be wireless, right? And the layers involved in this communication is usually the physical layer, which is responsible for all the actual transmission, like modulation, encoding, the physical connectors, everything, the signal, everything in that area. And then the data, we talked about the data link layer, which is responsible for ensuring that the um, data is received correctly on the other end. So the data link is responsible for framing, if we're talking about packet switching, framing the packets, sending them on the other side to the other side. We have these error detection techniques, the ARQ, automatic repeat request. All of these are responsibilities of the data link. And then we talked about multiplexers. So multiplexer is a way to share the medium between multiple nodes. So if we have multiple nodes here and we want to share a single medium, so we'll use a multiplexer and demultiplexer on the other side. And this multiplexing can be a frequency division multiplexer, which divides the bandwidth into multiple channels, or it can be time division multiplexing or wavelength division multiplexing, right? And in this case, we allocate a specific channel to every pair of nodes. And one disadvantage of that was if the channel is not being used, if the pair is not talking, then the channel will go unused. All right. So where LANs happen here? What is the purpose of LAN? So if we go to this LAN representation, and this is common for something like Ethernet that we use today, right? So the Ethernet started by having a topology like this, where nodes connect to a shared bus. It's really a wire cable that connects one one node to the other, to the other, to the other in a serial fashion. So you will imagine here there is a connector, a T connector that passes traffic to the node and then also continues to the other nodes, right? And physically you have to connect them one next to the other, right? So in this um, topology, we don't have a multiplexer that divides the time or the frequency among these nodes. Instead, what happens is any node can send traffic to any other node by putting the frame on the bus, right? And the bus in this case, the frame in this case has to have the address of the destination and also the source, right? So A wants to talk to D, puts a frame that has the D as the destination address and A as the source address, and the frame, the signal, will travel across the entire bus, left and right, right? along the whole length of the bus. What happened to the B, C, and D? They are constantly listening, and they're listening to the bus constantly. If they see the address, if they see their own address on the frame, they pick it up. They pick it up and they process it the usual way as we talked before. If B looks at the frame and see that the address is for D, it's not for B, it ignores it. It doesn't read it. Okay, so that's solves one problem. We don't have to have a multiplexer, and anybody can send data to anybody. But that raises a couple of problems. The first problem is, what if two nodes try to send the data at the same time, right? So that's impossible. The two signals will corrupt each other, and nothing will hear any, or nobody will hear anything. So you will see here B is sending, everybody else is listening, but what if A and B send at the same time? Well, we will see that this creates something called a collision, where two signals coming from two different sources, they will collide, they will destroy each other, and nobody's listening. Okay, that's one problem. The other problem is the topology itself. Connecting something like this, it's not practical. It used to be, actually. This is how the Ethernet started by doing a cable like this. But if I want to connect 50 cables, 50 nodes together, I have to run a cable that connects all 50 nodes in a bus situation, in one after another, so daisy chained. That's not convenient, and if I want to insert a new node in the middle, I have to break the cable, which means disconnect the network entirely, and then cut the cable, install connectors, and connect something in the middle here. So I have to disrupt the network. All right, so we have to find a solution to these two problems. The solution to the bus problem is actually easier. The solution to the bus problem happened by actually looking at, I'll explain it in a simple way. So we have this bus that connects nodes. So what if I shrink this bus, right, to the point it becomes a point, becomes like a single point. So this goes and becomes like this. So I transfer the bus topology to a star topology. And this is exactly what happened. Um, they created something called the hub, which is a device that internally it represents a bus, right? And these connections were made permanently into the bus. All I need to do is to connect a cable between the node and this device, the hub. So now I can install a hub somewhere in the network, and then instead of breaking the cable and uh, disconnecting the network every time I want to add a node, no, instead there are ports in the hub, and I can just connect the nodes that I want anytime I want them without disrupting the network. Internally, the hub works like the bus. So in terms of function, the hub and the bus are working the same way, which means that anything the node transmits, it will be listened to the entire, or everybody else will listen to, right? So we still have the problem of collisions, having two nodes talking to each other at the same time. But we solved the topology problem. Okay, so to solve the issue of um, collisions, we have to introduce something else to the layers that we talked about. So we talked about 7 layers, right? And I said that the data link layer is responsible for managing or for making sure that the frames can go from A to B or from one node to the other correctly. Now we have to add something else to the functionality of the data link. This something else is called media access control or medium access control. So we need to add to the responsibility of the data link, we need to add a mechanism that allows the nodes to share the same medium, the same bus here, without colliding with each other. So we take the data link layer and split it into 2 sublayers. One, we call it the medium access control, and the other one is called link layer control. So this link layer control does the same thing as the data link before, like it divides the, it does the windowing, it does the flow control, the automatic repeat request, and all of that, right? MAC layer takes care of accessing the uh, the medium itself, and maybe it borrows some of the responsibility of the data link, like the CRC, for example. We see it at the bottom layer. Okay, so how does the MAC work? So actually, we will talk about the MAC in the next lecture. So how we avoid collisions, we'll talk about it in the next lecture. Right now, we just need to know that we have layer 2 is divided into 2 sublayers, right? So this picture shows the 2 sublayers, and also probably noticed by now that every time I want to send, or because the layers are transparent to each other or they talk to each other directly, we always have the concept of the addressing. So when I send something from node A to node B, I have to attach an address so that we know where this frame is going, right? Within, when the frame is received at the destination, it needs to, the frame or the layer needs to know which protocol at the top layer this frame has to be forwarded to, or the payload has to be forwarded to. So the concept, actually, when we look at layers like this, they are not just one protocol. We have seen like the physical layer and the data link layer. Let me put them into the side here. And the network and the transport and so on. Each one of them actually consists of multiple protocols. Some of them we have studied already, but some of them we didn't. So when the frame comes and it's received by the data link layer, right? The data link layer maybe wants to know which network protocol it needs to forward the packet to. So we have multiple protocols. And also the network protocol needs to forward the payload to the transport layer. So we need to have a concept of ports or access ports or service ports, or basically another form of an address, that the address of the protocol that we need to forward the payload to. So The generic name for them is service access point, right? It's a port number. So we'll see here when we go up, when we talk about TCP IP stack, we have the concept of the port number, right? But the port number concept in general applies even to the lower layers. All right, so when we look at the encapsulation here, the application layer sends its data to the transport. The transport adds a header. It may need to segment the data into multiple segments, right? The passes the traffic to passes the payload to the IP layer and then to the LLC layer, then to the MAC layer. So here, because of we have the we have divided the data link into two sublayers, each one of them will have its own header, all right, to maintain the same concept of transparency that we talked about. So if you look at it now, my frame has the MAC MAC header, which has the MAC control, and then destination and source. So we have the MAC address, which is something that you probably become familiar with. The MAC address is the address that we use to uh, identify the nodes, the physical nodes. Each physical node, each port, each network card has a MAC address which is given by the manufacturer. We can modify it, we can change it, but it's usually assigned by the manufacturer. And the MAC address is supposed to be universally unique, so no two MAC addresses are the same. But as I said, we can change them. Right? And the MAC frame also includes the CRC at the end here. All right. And the data or the payload inside the MAC frame is the LLC PDU. So the LLC PDU also has source and destination addresses. We just call them service access points, right? Destination and source, that they point to which service or which protocol the data is going up to or down from. And then we have the LLC control. And then we have the payload, which is the what's coming from the upper layer, which is the IP layer, right? Or the network layer. Okay, so this is the general idea. As I said, in the next lecture, we will talk about how to manage this um, um, medium access control and the collisions and all of that, right? But for now, we're going to talk about something else. We're going to talk about bridges. So if we go back to this picture here, one of the issues I mentioned with this is that um, it's the scalability. If I have 50 of these, F50 nodes, I have to daisy chain each one of them one after another, one after another, one after another. That's a problem. We avoided some of the problem by putting um, a hub here instead of a bus. I still have a scalability problem though, even with the hubs. Um, the problem is there is a limitation of how many nodes I can attach to the network. The limitation comes from a distance and also comes from um, because this medium, the bus or even the hub, uh, has a limit on how many nodes they can be connected to it. Why there is a limit? Well, imagine there are two nodes connected to the bus. Well, the two nodes, when they talk to each other, there is very little chance that their traffic will collide with each other, especially if the buses actually allow only for uh, one-way communication, so it's not full duplex, right? So it's half duplex. Buses will allow only half duplex because you can put one thing on the media, one thing at a time, right? You cannot have two-way communication. So there are two nodes talking to each other. They have to take turns, right? Sharing the or accessing the medium. All right. If the two nodes become four, it becomes harder to share the medium because we have more nodes. If the four become 8 or 10, it's even harder, right? So the more nodes we put on the bus, the harder it is for them to share because there's so much request to access this shared medium. And also we have physical limitation. The signal we saw that there is a propagation time for the signal. So if I imagine having a bus that has a 100-meter length, the signal that goes from one point to the other may cross it in a short time. If I increase this because I have more nodes, so I increase the 100, it becomes 500 or 1 kilometer, the signal will travel a lot further. So that creates a problem. So we have problems with this bus topology. So one solution to this problem is to create something called bridges. So the idea of the bridge is we use the bridge to break the network into smaller segments. So instead of a bus that connects nodes like this, I may come and say, well, I'm gonna put a bridge here. Okay, what's the benefit of the bridge now? Why did I put the bridge this way? The first benefit I can notice is that now I have two segments instead of one. And this segment is separated from this segment. The nodes in the left segment, they can talk to each other, they can share the bus. So now there are, instead of 6 nodes sharing one bus, we have 3 nodes sharing one bus and 3 other nodes sharing the other bus. So now the possibility of having collisions between the nodes is less, right? And sharing the bus becomes like you're sharing the medium with fewer nodes, so you have better chance to access the medium because we are sharing with lower number of nodes. Okay, the other thing is now because we are sending electromagnetic signal along the bus. This signal is subject to noise, subject to distortion because of other factors. If I split the bus into two, anytime A wants to talk to F here, the packet can go to the bridge. The bridge can look at the data, clean it up, right? Read it, and send it back as brand new frame on the other side. So in other words, we avoid um, um, the signal is retransmitted, but we don't retransmit the noise, we don't retransmit all the other problems, right? Um, in general, if I want to send something along long distance, well, you know that the signal will fade over time. So I may need to have a repeater. The repeater will look at the signal and amplify it and send it on its way. Amplifiers usually, or repeaters, what they do, they amplify everything, including the noise. Bridges, on the other hand, they will read. So we don't use amplifiers in LANs. Instead, we use the bridges. The bridge is like any other node. It will read the data look at it, check if there is no errors in it. If there is errors, we'll drop it the same way. But if there are no errors in it, it will retransmit it on the other interface. So when the signal is retransmitted on the other interface, it's retransmitted as brand new frame, right? So without any um, noise in it. This means that I can extend my network much longer than a single bus can. In fact, early Ethernet, you can have it extended. So the bus itself, I forgot what the number was, but I think it was up to 100. You cannot have more than 100-meter bus. And then, but you can use um, up to 3 bridges, so you can connect 100 meter to another 100 meter, so you extend the bus into 500-meter network. So 500 meters could be useful for a large building, right? Anyways, but the bridges don't come free. They have their own problems. So we'll talk about these. But still, there are more advantages to the bridges. Let me see. Let's go back to the slides and see what kind of advantage that the bridges provide. So I'm going to talk about the reliability advantage later, but we talked about performance. So when we divide our network by bridges, we have smaller buses, and those smaller buses allow nodes to talk to each other. They have more chances to talk. So the performance, the amount of traffic that can be transmitted goes up. Security, important as well, because now each one of these nodes or segments, their traffic is isolated from the others, right? We saw earlier that if one node sends something, everybody listens. Everybody listens. That's the nature of the network. Everybody listens, and we rely on um, the the fact that the protocol will pick only the frame that is destined to itself, right? But that's actually can be changed by software, and we can pick everybody's traffic, and this is how packet sniffers work, actually, by listening to everybody. If I add bridges, this problem becomes less. It's not entirely eliminated, but it's less. So the traffic here is isolated from the traffic here. So if A wants to send something to C, F won't listen to it, won't be able to listen to it, because it's within the segment, right? Now the bridges will send something, but that's another issue. Geography, we can extend the reach of the network using bridges. So what is the issue here? What we talked about reliability. What does it mean to have reliability? There are actually two reasons for why the bridges increase the reliability. The first one is back when the network was a bus network and something happens, there is a disconnection somewhere. Like if the network disconnected here, what happen is the whole network fails. Right? The whole network fails. Even the part that are still remain connected. So if there is a cut here, the whole network is down. The reason is actually the network has to have resistors here, terminators we call them, and if you cut somewhere here, there will be no terminators on those ends, so the network will not work, right? Now if we do bridges like this, and we have a cut somewhere, the other segments will not be affected. They will still work fine. The the part that has the cut will fail, but the other parts won't. And there is also another reason bridges increase reliability. Let's say I connect these two bridges this way. So now the bridge will have three interfaces. So in this case, if let's say node, we'll call it X and node Y, if node X and node Y can talk to each other, they can before, right? So they still can, and we will see later that bridges will forward the frame. So A can or X can talk to Y across this network by passing the traffic from one segment to the other, right? But if there is a disconnection here, and I keep forgetting to disable my eraser, if I have a disconnection here, X won't be able to talk to Y. Now each segment can still talk to other nodes in the same segment, but across the segments there will be a break. If I make this connection, then X will have another route to talk to Y. So now I increase the reliability of the network, and this is one of the advantages of the bridges. Okay, so we talked about the bridges. So how do they work? So let me just go over the slides, make sure that I didn't forget anything. Bridges can connect two LANs of the same technology, but they can also connect two different LANs of different technologies, right? So we will talk about this when we talk about wireless. On here actually they may talk to LANs and WANs, so normally we'll talk in this lecture about the two segments of the same technology, but it is possible to have a bridge that connects two different technologies together. And there is a mention also in the slide about we don't need a link layer protocol, and this is correct. When we have a bridge, the bridge will include physical layer. Why? Because we need physical connections, and we need to have a MAC layer. Right? The bridge take a frame from one side, pass it to the other frame, other side, right? So what does it mean that it doesn't have LLC? It means that it won't participate in windowing, it doesn't participate in ARQ, it doesn't do anything. It just takes frames from one side, pass it to the other side, right? So the bridge is transparent to the network. The same as the multiplexers when we talked about multiplexers before. So the bridge is totally transparent. A here and F here will not feel that there is a bridge in between. The bridge does not work at the data link layer, so A still wants to talk to F, still exchanges the information from with F. The F or A both participate in, if we use HDLC as we talked last lecture, then they will participate in the windows, they will participate in error detection, they will be participating in all of this at the LLC layer. The bridge does not participate in that. The bridge just makes sure that the MAC is received correctly the MAC frame is received correctly and send it to the other side, right? So that's what it's meant here by in this slide. Forgot which slide it was in, but anyway, there was a slide that says it has only the MAC and the physical address. And this is the functionality of the bridge. The bridge sits between two LANs. It reads all frames transmitted on one LAN and accepts those addresses to any station on the other LAN. Using the MAC protocol for the second LAN, it retransmits each frame to that LAN. Okay, so let me explain that. So A wants to send something to, or station 1 on LAN A wants to send something to station 11 on LAN B. So A put the frame on the bus. Station 2 to station 10, they won't read the frame because it's not addressed to them. The bridge look at the frame and say, okay, this frame came from LAN A, so what I'm gonna do, I'm gonna pass it to LAN B. Now once it passes the frame to LAN B, now station 11 looks at the destination address and say, okay, yeah, this is mine, and it will read it. Same thing, station 11 wants to reply to station 1, so it sends the frame, the bridge reads it and pass it to the other side, right? So the bridge in its simpler function, it will just look at the frame coming from one LAN, it passes it to the other LAN. What if station 1 sends something to station 10? Will the bridge pass it to LAN B? Yes, it will, right? And if we look at this basic operation, if station 1 sends something to station 10, the bridge will pass it to LAN B, even though actually station 10 is in LAN A and nobody will need it to LAN B. So this simple mechanism needs a little bit of adjustment to make sure that the bridge doesn't forward packets just unnecessarily to other sides, right? So now we have something called MAC table, or we'll call it, here the slide says routing intelligence. So how does it work? Let me see. Let's take a look at a simple, this is LAN A, and this is a bridge, and this is LAN B. And let's say this is station 1 and this is station 2, and this is station 11 and station 12. All right? So the bridge, to avoid sending information unnecessarily to other LANs, it maintains a table. The table has the MAC address of the station and the port where it came from. Right? So if 1 sends packet to 11, so that's the packet with 11 as destination and 1 as source, the bridge initially will look at the frame and say, do I know where 11 is? I look at the table and the table is empty. I don't know where the frame is, where 11 is. So what I'm gonna do, I'm gonna send the packet to the other side. Now, of course, if it was received on port 1, it must be transmitted only on port 2. It cannot be sent back, right? So the simple mechanism of the bridge. If you receive a packet from one port, you don't send it back to the same port. You send it back to other ports, but not where it came from. So that applies if the bridge has multiple ports and the packet came from port 1, it will send it to all other ports except one. So it will send it to 2 and 3 and 4 and all of that, but not the source. But right now we just focus on the example of just 2 ports to make it simple. Okay, so the frame is sent here. Oh, by the way, so this frame was sent to LAN B. By the way, in this process, the bridge says, but now I know that this frame came from station 1 on port 1. So I'm going to write station 1 here, and the port that came from is 1. So the bridge learns where the packet came from. It doesn't know where the destination is. It doesn't know where station 11 is right now. But the packet came from port 1 coming from station 1, so it is recorded here. Okay, so now the packet is sent to LAN B. LAN B, eventually it will send the frame back to 1, right? So usually there is a reply. So the reply will go with the destination is 1, the source is 11. So now the packet comes to the bridge. The bridge says, I know where the destination is. I know where 1 is. It's already recorded here. So I'm going to send it to LAN A. And I also learned that 11 resides on port 2. So both stations are recorded. Okay, so now let's see how that's helpful in the future. So now the bridge learned about 2 stations, 1 and 2. Now let's say again station 1 sends packet, but this time it sends it to station 2. So the destination is 2, the source is 1. The bridge look at it and say, bridge, the destination 2, I don't know where it is, but I know where the source is. So I am going to, the source is already recorded. So I'm going to forward the packet to all other ports. So I'm going to send the packet to LAN B, right? Because I don't know where 2 is. 2 eventually replies to 1. So it puts 1 as the destination, 2 as the source. The bridge reads this packet because it's on the same segment and say, okay, now I know 2 is coming from port 1, and I know that the destination 1 is also on port 1, so I'm not gonna forward this packet. I know where it's on the same segment here, so I'm not gonna forward it to segment 2, right? So this mechanism happens every time a packet is sent from one of these stations. The bridge receives it and learns about where the source is coming from, even though it doesn't know about the destination, but it knows where the source is coming from, and it will keep updating its MAC table. Eventually it will know about all the stations and whether they are located on LAN A or located on LAN B. So and we can actually even replace this with LAN, so we make it clear: LAN A, LAN B, LAN A. Usually it's about ports, not LAN, but just to clarify it. So that's what we'll call address learning mechanism. So the bridge initially will use the flooding mechanism. So the flooding means any unknown packet, it will be just sent to all the ports except where it came from. But after a while, the bridge will know where each station is because it keeps listening to the packets and it fills its table. So it doesn't need to flood the network anymore. All right. So that's the mechanism that we use. And if you go to any modern switch, there is the modern switches, by the way, are just bridges with multiple ports. So they have MAC tables. And if you do it in the lab and just try to display the MAC table on your switch, you will see uh, each MAC and the port where it came from. Uh, this mechanism, the MAC learning, is good if I look at the network that I just showed you on the slides. It's good for in a situation where I have a network like this. All of these are bridges, and station 1 wants to talk to station 6, station 4 wants to talk to station 3. So initially, the bridge 101, for example, looks at the frame and says, I don't know where the destination is, so I'm going to send it to the other port, right? And it will continue doing this, sending the packet. So bridge 101 sends the frame to LAN B. Bridge 103 and 104 looks at the frame and says, we don't know where the destination is, so we're going to send it to the other ports, LAN D and LAN E, and eventually the destination will receive the frame, right? Because the bridges will flood all of these frames continuously until the destination receives it. So it's a good mechanism. And gradually, the bridges will learn where the frames are coming from. So they will um, stop doing flooding after a while. So if every bridge fill its table and knows that station 1 is on LAN A, station D on LAN, station 4 on LAN D, and so on, they will stop doing the flooding unnecessarily. So the flooding happens only when the bridge doesn't know where the destination is. All right, but that's not the only thing that we need to worry about. Let's see a situation where we have two bridges connecting two LANs. So bridge 1 and bridge 2. And here is LAN A and LAN B. And we have, let's keep the same stations, station 1, station 2, station 11, station 12 or 10. So we have, this situation creates a problem. Let's look at the problem. So A sends a packet to 11. So it puts the destination here, it puts the source here. Both bridges, bridge 1 and bridge 2, because they are on the same segment, same LAN segment, they will hear the packet and they don't know about the other bridge, so they will act like they are the only bridge in the segment. So bridge 1 has a MAC table, bridge 2 has a MAC table. Bridge 1 say, oh, I received a packet going to 11, but I don't know where the 11 is. So instead of port, just we put the LAN here. So I don't know where 11 is, so I'm gonna send the packet to LAN B, and also bridge 2 acts the same way. It sends the packet to LAN B, right? And both of them record, okay, so station 1 happened to be on LAN A, station 1 happened to be on LAN A. So first problem is, I'm just gonna make a difference here. So bridge 1 sends the frame, and this is green, sends it to LAN B. Bridge 2 sends the same frame to LAN B as well. So now we have duplicate frames going to LAN B. This is my first problem here. My second problem is, once the frame, the green frame, is sent to LAN B, bridge 2 will hear it, same thing as all the stations will hear the frame. And this is, so bridge 2 thinks, oh, this is frame, a new frame going to 11 coming from 1. So, but 1 was recorded earlier that resides on LAN A. So I'm going to update my MAC table here and say that station 1 is residing on LAN B. Why? Because I received this frame from LAN B and it says the source is 1. So the station 1 must be in LAN 1, in LAN B, right? And then what it does, it sends the frame, because it doesn't know where 11 is, so it sends the frame back to LAN A. Bridge 1 does the same thing for this red packet here. It says, well, this is a new packet, and same thing. I thought station 1 was residing on LAN B, but actually it's not. So it is actually residing on LAN B. Instead of LAN A, it's residing on LAN B. Why? Because this frame came from LAN B. So I'm going to update my MAC table, and I am going to send the frame to LAN A, because I still don't know where 11 is. And this happens, so now bridge 1 sees the red frame that came from bridge 1, so it circulates it back, and this will happen, creates a loop and creates duplicates. So you'll see that every time the frame comes to the LAN, the bridge reads it and thinks that, oh, this is a new frame and I don't know where the destination is. I'm gonna send it to the other LAN, and it will keep doing this, and this will, in a matter of seconds, it starts with one frame and it explodes in packets. It will duplicate and duplicate and duplicate. So the first packet was duplicated twice, became 2, and then each packet, the green and the red, are duplicated again and duplicated again. So it goes exponential. It goes from 1 to 2 to 4 to 8 to 16, and in a matter of seconds it may destroy the network. So loops are one of the worst thing that could happen to any network. We don't like them in networking at all, right? Um, I would say, okay, why we are putting glue or bridges in the first place? Well, this scenario is useful for redundancy. It's useful for reliability. What if one bridge fails? I'll have another bridge, right, to connect between the two LANs. The scenario that I explained here, right? So we have this segment that will make the X and Y communicate, even if there is a failure in between. So we create loops because we need reliability. We need multiple paths, multiple routes between any two LAN segments. So they are useful, but they carry the risk of packets going back and forth, not back and forth, but going around and around and around, right, and duplicating in the process. So we need to have something that keeps the loops but prevents this ugly scenario from happening. So to do that, we have to rely on another mechanism in addition to the Mac learning. We need to break the loops. So if I have a network, let me draw a network in a different form. So if I have a network that consists of multiple loops, these are bridges, right? And these bridges are connecting to each other. So from the reliability point of view, this is a great network because it has multiple paths. But if I don't solve the loop problem, then any packet coming from one segment, it will be replicated in all of these segments and it will loop forever and it will destroy the network. So I need a solution. And the solution is by creating something called spanning tree. So the spanning tree is a mechanism that allows the network to convert a loop like this into a tree. A tree doesn't have any loops by definition. So I may create a loop by saying, here is my tree, right? So under normal circumstances, the traffic will go only through this red segments. So we'll call, and I may extend this a little bit, so it's like this. Let me draw it better. I'll explain why I'm doing it this way. Okay, so this means that if there is a station here that wants to communicate to a station here, the traffic will follow this path, right? Let me do it in green. So the traffic will go this path. It will never go this way. So why? Because I block these ports. These ports on the bridge, they don't participate. They don't receive any packets. That's why I put this red circle here, right? So the red circle represents ports that are blocked from the bridges. So if the bridge has a port that's blocked, that's physically it's still active, but it doesn't receive any packets. So now there is no situation where the bridge receive packet from two places at once. You will see here that this situation never happens. So I have a station here that is connected and there is two bridges, but this bridge this bridge becomes dormant or doesn't participate in this segment. All the traffic will go to this bridge, and this bridge will take care of sending the traffic to other segments, right? So any network with two bridges, one of them is blocked, one of them doesn't participate, right? um, there are exceptions here. So this bridge, one of so we have something called the root bridge in the spanning tree, right? So a spanning tree is one of the most important technologies and protocols that you have to understand very well. And based on my personal experience, it creates a lot of problems in networks if you are not careful about them. We talk a lot in networking field, talk a lot about routing, and there is a lot of focus on routing. But in reality, switch networks are a lot cheaper and a lot more um, common, right? So even though we talk about a lot about routing protocols, a lot of networks in out there, they are mainly based on switches. And if you're not careful about spanning tree, you you, you have trouble, right? So spanning tree is very important to understand. We will talk about spanning tree more on the physical and data link course, but just keep in mind that you have to understand spanning tree very well. All right, so um, let's go back to the slides and see. So we have a situation here where if you look at this line where I'm tracing my cursor here, so bridge 1, bridge 101, bridge 104, bridge 107 create loop. So in this case, it is possible for a packet that's coming from station 1 to be replicated to LAN B, and then replicated back to LAN E, and then replicated back to LAN A again because of the bridges. So we need to put a spanning tree to prevent that from happening. This slide says that we can do fixed routing. So what we can do is tell the bridges don't ignore this port or forward the packets. So what we do is make this permanent, make these MAC tables permanent. So we program them ourselves, and when we program them ourselves, we may prevent some of this from happening. But dynamic networks are not a good idea to program something permanently in a dynamic network. Why? Because as I said before, we need the loops for reliability. So if I make this tree permanent, what happens if a link breaks? The network does not adapt. But in case a link break, let's say this this bridge fails, right? So the spanning tree rearranges itself and the traffic now goes this way, right? So any node that happens on this segment will find another way to pass traffic. And that's the benefit that we get from dynamic networks. So although fixed routing is a solution, but it may not be always a good solution. So we talked about frame forwarding, address learning, and loop resolution. So all of this we talked about. So the forwarding idea is that the bridge will see packet coming from one port, it will send it to other ports except the one that it came from. The address learning, we need it so that instead of flooding, which is not a good idea, Not as bad as loops, but it's not a good idea either to continue flooding the network. So the bridge needs to learn how to forward packets accurately by learning about their MAC address, right? And then finally, we talked about how to prevent loops by using the spanning tree algorithm. So this is, by the way, I didn't mention how do I create the algorithm? How do I create the spanning tree? This spanning tree. We created using a protocol that is exchanged between the bridges. So the bridges will send each other information, exchanging information about themselves, and they will build the spanning tree among themselves. So this is not something that nodes participate in, it's just the bridges among themselves. And the spanning tree protocol is one of those protocols that work on layer 2, right? So the bridges learn about themselves, and then they decide so which port will be blocked. Okay, so and we will leave this to other lecture, the spanning tree detail itself. So we talked about hubs and switches. So what is the benefit of hubs and switches? So we saw that if we have a hub here, we can connect nodes to it. But as I said, the hub is still, in theory, it's still just one segment, one bus segment. So all traffic is shared. So if we have 10 megabits per second network, these four nodes will share the 10 megabits per second. So if everything is equal, each one of them will get 2.5 megabits per second, in theory, right? The benefit of the hub is I can extend the network. I can say, well, how about I put another hub here and connect these to another four, right? So I have a hierarchy. That's also possible. So with the hubs, I can extend the network, but still all the nodes will share the 10 megabits per second, no matter what, right? So because it's shared media and it's half duplex, right? So only one node can talk at a time. Now, the technology expanded. So when we used bridges, the bridges are not hubs. The bridges is a device that works on the MAC layer, and it can receive a frame from one side, send it to another side. How about I add more ports, which I hinted to before. So now I have port 1, port 2, port 3, and 4. Same thing, a frame can come from one port and go to any other port, right? And we have this forwarding mechanism and address learning mechanism to tell the bridge where to forward packets. If I expand the bridge and have 12 ports instead of 4, right? Now we will call this a switch. So actually, if you look at the standards, the IEEE standards, there is no mention of a switch. There is a mention of a bridge. The switches are just bridges with multiple ports, right? So how is the bridge again different from the hub? Okay, so if this network is 10 meg and this network is 10 meg, right? The bandwidth for each. So now we have two networks, each one of them with 10 meg. If this network, if this segment has 4 nodes and this segment has 4 nodes, each node, now we have 8 nodes, but each node will share 2.5 meg, right? If I put more nodes here and more nodes here, I have, in total, I have 40 meg, and we have 16 nodes. So actually, now by using bridges or switches, I can um, extend the bandwidth of the network as well, because each one of these ports connect to a segment that has 10 meg bandwidth. Now, switches nowadays, they don't have multiple nodes connecting to them. Instead, they have only one node, only one station. So if this LAN segment here has 10 meg bandwidth, and this has 10 meg, and this has 10 meg, so each node will have a full 10 meg bandwidth to itself. Another advantage of using the bridges is actually I can do, if I guarantee one node only in each port, I can create full duplex communication. I can make sure that um, between any two nodes, I have two paths, one for transmission and one for reception. So I have full duplex communication, which practically means that each node will have 20 meg of traffic available to it for each direction. So we come back here and see, okay, so the hub will have shared medium. The switches will have, instead of sharing the medium, it will divide the medium into multiple segments. Each segment will have the same bandwidth. And we can build the hierarchy as well. And we can um, um, eventually create a topology like this, where we have multiple switches. Each one of them will have a separate LAN, right? So switches will have the same address space. What does it mean, same address space? All the addresses, so if I send something from X, it will still be received by W, still will be received by Z, still will be received by Y. So we have, because they all will share the same data link layer, right? If I wanna, if I want to have a broadcast, or if W sends something, it will effectively be broadcasted to everybody. Everybody will listen to it, right? That's actually slightly untrue. It happens initially, but the switches will, because of the learning, will stop the flooding eventually. But broadcast is still possible on layer 3. So if I want to intentionally send broadcast to everybody, I can still do it, right? What else? I forgot here. All users share common MAC broadcast. So that's what I just mentioned. It is possible that I can send a broadcast to all stations connected to all these switches. Because of the spanning tree protocol, I can have only one path possible. I cannot pass traffic through multiple paths, even if it exists. Why? Because we will have loops otherwise. So here, like any node that resides on this segment, for example, will have, in theory, will have multiple paths that go to another segment, but we cannot use them, right? Because if we use them, we will have loops. So we have to be careful about that. And we can partition a LAN using something called virtual LANs, or using routers. So virtual LAN is here, but a router, I can convert this. So this will be the same broadcast domain, right? So I can split it into multiple broadcast domain by putting a router. The router will not pass any broadcast. The router has to have a specific IP address to forward to. So W, if it tries to send traffic broadcast, it will be listened to by the stations of the same connected to the same switch here, but it won't go to other switches, right? So to send something to other switches, it has to send a particular use a particular IP address to pass. So routers will not forward broadcasts, and routers used to limit broadcast and limit flooding. Flooding is needed to forward the packet into multiple stations initially. All right, and I mentioned here the virtual LAN. We'll talk about virtual LANs later, but the virtual LAN divides the switch into segments. So here, for example, I can say these ports belong to one LAN and these ports belong to another LAN. So I use the same switch, but I divided the network into two different LANs. So the nodes that reside on LAN, the red LAN, will never be able to reach the green LAN and vice versa. They are totally separate from each other, right? So the only way I can connect them together if I can put a router. So if I can put a router here between the two, so now the green and the red can talk to each other, but otherwise they will be totally separated, right? So the advantage of the LAN or of the VLAN, so we use VLANs a lot in networks. We hardly build any network without a virtual LAN nowadays. And the reason is they are flexible. It can allow us to divide the network into multiple segments based on departments or based on job function or based on geographical location, based on many things. So it will allow us to use switches, but then divide the LAN into multiple segments, and each one of them will be separated from the other. The connections between the switches, if they carry information between multiple VLANs, we'll call them trunks, right? So that's other details that's not covered in this lecture. So that's what we need to know for now. And that's all about LANs. We will talk about other details in the following lectures. And for now, thank you very much, and I will see you in another recording.